Sorry. Hi, my name is Hannan. I'm the Director of Network Architecture at Frontier GlobalCenter. What we wanted to do was to kind of give a case study, not so much like a background information or not so much what Sprint's doing, but kind of a case study of what a Greenfield network is and some of the trials and tribulations you go through. I don't really like the term Greenfield network, but it seemed to come to mind. And lots of vendors come to me and they want to sell us stuff, and they always say we're a Greenfield network. And I guess you would kind of put people like Enron, Williams, Level 3, Quest, and Frontier as kind of a Greenfield network because we're kind of starting from the beginning. It's like you have a greenfield and you get to start from there. So it's subtitled, How to Go from Fiber to MPLS in 1 year. Now, in theory, this is going to be online, but I broke it. Okay, so here's the agenda. What I'm going to do is just run through some stuff, and I'm pretty interactive, and I know it's kind of awkward to, to like ask questions in the middle, but please feel free. And I'll try to run through this in just a bit of time, and then maybe we'll grab all the positive MPLS people back up, and we can talk a little bit more. So we're going to run through here just how we started off, some of the decisions we made, some of the challenges we had, how we're doing things now, and kind of a snapshot of where we're at. And again, the message here is you hear a lot about new ISPs starting up. You hear about all these people with all this fiber, and this is kind of a case study of what we went through, starting from the beginning, getting to where we are now, which we're pretty proud of, and our network is not 1/6 the size of Sprint. Okay, so in the beginning, I actually joined about 1.5 years ago, and there were 4 companies, ISI, PrimeNet, Voyager, and FrontierNet. They were separate networks, and one of the big tasks we had was putting them all together. We had new bosses from Frontier, and learning how to work with them wasn't that difficult, but it was certainly part of the overall challenge. So we had to merge the ASs, transition IGP from OSPF to ISIS. We built the team up to where we have a real strong team now, and planned the new network build. And that was a real challenge as well, because we got bought by a bunch of telco people, and as Peter knows, telco people are ATM people, right? So we had to convince them that ATM wasn't necessarily the way, the truth, and the light. But we seemed to have done a pretty good job at that. But there was a lot of religion, and at one point our CEO, Joe Clayton, I remember the quote, he said, "God damn it, build both." So we just built one IP over WDM network, and we built one ATM over WDM network. And that way, we feel that was a real good decision for us because we were able to build both of those as purely as possible. So we built that out, and one of the sticking points we made was that we wanted to build a pure IP over WDM network because we felt that by the time we needed to constrain bandwidth in the network, we would have technology available to do MPLS, something that Peter was ribbing me about a little bit. So hopefully I'll prove the point that MPLS is a useful thing. Okay, so we started off with this, and I want to apologize. I had this all set up for 1024 by 768. It looked pretty neat, but now you can just kind of barely see it. Frontier hired Quest to build about 17,000 route miles of fiber. We then went out and swapped out about another 4,000 to where today we have about 21,000 route miles all over there. Each one of those black lines, with a few exceptions, represents 24 strands of fiber. And I believe that's mostly Lucent True Wave or whatever Corning's equivalent is to that. So we said, we got this fiber out here, and let's see, I think Dave Siegel and I were kind of the folks, and Wayne and John were all there. We hadn't brought everybody on board. We started thinking about how to make this stuff happen. And you start off with this as an ingredient, just like Peter was showing all the buzzwords you have, and you say, how do you make the best network out of it? Well, one of the things we had at this time was a really good transmission group. And the transmission group had built out a WDM system using NEC gear, which could do 16 lambdas. And they made the decision to use, this is back in 1997, early 98, to use NEC at OC48. And some of our competitors like Quest and some others chose to use OC192, and we kind of poked fun at them because they went out and built out these big OC192s, which took up half the rack space, and then they had to buy these big ADMs that went from OC192 back down to OC48 to make it useful. But we started off with OC48, and I think you've been inundated with WDM in the last couple hours, but the main thing is that you can pull out lambdas or individual colors, and you can actually plug those into equipment. So that's what our focus was. Plug them into Titan Muxes, plug them into the ATM switches, and plug them into the routers. So we made a hub, and we say this is what a hub looks like. Basically, we wanted to build a hierarchy in and make it really robust. So we said, let's build things in pairs, because like Peter was alluding to earlier, the routers are not absolutely stable. So we wanted to be able to build a network that could sustain a backbone failure, but the overall network health would remain. And we think we did a great job. Basically, what we have is what we call a WAN router, a WR in pairs, what we call a CR, a core router, and then what we call component routers here at the bottom. So each router at the bottom has a certain role. It might be focused on aggregating dedicated customers or on peering or on anything else like that. So it's capable of OC48 at the top, OC12 down to the middle layer, and OC3 at the bottom layer. And what we found is that we're at the edge of that scaling. We actually have to start going OC12, and then your hierarchy starts breaking apart, which is a challenge right now. And we built a network design, which basically has 3 OC48 rings, one of them here between San Francisco, Los Angeles, Kansas City, and Houston, another one between Kansas City, Cleveland, Atlanta, Houston, and finally a triangle between Cleveland, New York, and D.C. The blue is OC48, the red is OC12, green at OC3. Now, there's some interesting challenges you have here. For example, people laugh, what's so great about Cleveland and Kansas City? Why would you choose to put big circuits there? And there's not a whole lot of technology business in Cleveland. But what we found was that at the point in the build-out where we were, Chicago was effectively a stub. So if we wanted to run an OC48 through Chicago, we'd have to do from the backbone, let's see here. Go away. There we go. We would have had to have gone from the backbone up to Chicago and back down there, eating 2 units of fiber there. So sometimes when you wonder why people build networks a certain way, that might help explain some of the issues. Alrighty. So this is what the network looks now, and it's not a super granular picture, but right now we have an OC48 ring up between San Francisco, Los Angeles, and Kansas City. That Kansas City to LA circuit actually runs through Houston, but our Houston hub isn't completed yet, so it's concatenated there. We then have OC48 cross-country from San Francisco to Kansas City to Cleveland to New York. This is the New York metro area. And then OC12 ring on the East Coast and OC12 back on the West Coast. One of the things that points out here is that this is actually IP over WDM. So what you see right now is a single path. The initial build is the single path. Starting the third quarter, we do the second build, very similar to what Peter was talking about, where you might have the west router coming into your first WR and the west circuit coming into your first WR and the east circuit going into your second WR. Alrighty, so I talked about how Chicago's off the main route. A year and a half ago, OC48 was a really neat thing. It was brand new, and you weren't sure when the vendors were going to hit the timelines. But really being bleeding edge there, we had a lot of risks we had to take. When we finally got the stuff from the vendors, we tested it out, and it was really anticlimactic. The stuff just worked. We got it from, we used Cisco and Juniper, and the cards just worked just fine. So we were real happy with that. No SONET optics problems or anything like that. We were real worried about signal loss and framing and things like that, but it worked. The real challenge here, I started off at MidNet back in '94, which is an NSFNet, and to me, Internet was like a video game. You just would log into routers and configure stuff, and it was neat. And I never really had to worry about physical issues. But when you do a large-scale deployment, and don't get me wrong, about 3 months after I was there, I had to deal with physical issues. But it's amazing to me how significant the physical issues are for building out a large network. Finding space, getting power, getting your cabling and fiber things set up so that they work is really, really tricky. So we also were concerned about the diameter of the network, and I sent a note off about a year ago, maybe 9 months ago, about how packet over SONET could be a problem, because if people want to embrace packet over SONET, they're going to add more IP hops. And I think I got about 7 responses, and they all said I was silly, and Sean Doran said something other than that. But this actually became a problem for us a few months ago, insofar as customers that use Windows 95 have a default TTL of 32, and at certain places on our network, the diameter was about 17. So actually taking that up, 17, 30 seconds, is a little bit more than half. It really limited the size of the network they could see, the size of the internet they could see. We also interconnect IP and ATM at 12 locations, so that we have circuits, so customers that want to choose ATM can actually hop onto the IP network. And as far as APS restore time, maybe we can talk about that in the panel afterwards, because I'm sure Peter and I have some thoughts on that. But the focus here for us, I think I have a picture coming up soon. Let's focus on using MPLS to do fast reroute. We'll talk about that in a second. So as far as deployment issues, we spec'd out 10 racks for the major hub because we wanted to build in for growth. And it was really frustrating waiting for those to get built and the stuff moved around to have that. The site techs, I'm recruiting real heavily here because we want a lot of smart people. It's hard to find smart people at this level, but it's also real hard to find smart people at the SONET level, people that know how to plug fiber in and do BERT tests and things like that. Being in the COs, we weren't there on site, so we were kind of guessed. That was interesting. Getting the DC power plant built out, and even things as small as getting fiber from that corner of the CO to this one. Just learning how to work all that was different from the internet that I grew up with. Alrighty. So remember a little bit ago I said that we made the assumption that MPLS would be available for us by the time we needed it, and what we found is that was we just made it. So, let's see here. Today in the network, and this has been fairly constant for the last 6 months, we have about 250 routers. Of those routers, about 175 run ISIS and BGP, so they're real routers. The other one's kind of off to the side. About 1,000 backbone links in the network, including the LAN links local, and about 20 major hubs. So this was kind of our target. We wanted to kind of pick a point that was about second quarter, year 2000, and a certain amount of traffic and a certain network topology, and that was kind of our target design point. So we said, we've got 2.5 gigs of traffic going out of the network. We've got about 8 gigs of peering capacity. We're going to build the backbone out at OC48. How do we take the traffic that's offered onto the network and optimally fit it to the capacity that we have? Now, Lothbrogson would say put more circuits in, but I live in the real world, and that's kind of difficult. So you want to do better capacity planning. You want to get ahead, but sometimes if you don't have it here, you can use it elsewhere, and you really want to take advantage of that. So this is not a vision test. This is the ideal network topology. Oh, wow. Can we move that down a little bit? Maybe not. Oh, well. So the idea here is that in a given geographic region, you'd have a certain number of cities where you want to interconnect. You may have different customer demands in each city, but ideally you're going to have red and green cities, and in certain metropolitan areas you're going to have a moderate amount of capacity between each city. So, if this is the United States, this is the DC area, this is New York, this is Seattle, the Bay Area, you're probably not too concerned about the Kansas City area. This is what we're looking at. And what you want to do then is divide them into geographic regions and designate certain cities as transit cities, and leave other cities, like the green ones, as metropolitan cities. So that if one of the red hubs were to break, there would still be another hub in the metropolitan ring to carry the traffic out. So in a traditional IP network, if you want to go from A to B, or B to A as it actually reveals itself, you make a hop-by-hop routing decision, which everyone's real familiar with. What we'd like to do instead, however, is use MPLS to create regional paths and transit paths of how traffic will flow on certain router pairs. In addition to that, we want to be able to construct a backup LSP path such that if the head end of the LSP recognizes there's a failure, it'll fall over to the backup one. This is just another view of the network topology. And if you put these things on top of each other, you can imagine it scaling very, very high. So, really have to embrace the hierarchy. A lot of people don't get that, and I think it's going to cause a problem. But our target, again, looking at like second quarter 2000, what we want to design for is about 300 routers. So if you take 300 routers and you assume a uniform distribution, you'll end up with about 30 in each of your 9 or 10 geographic regions. If you designate each router as either being in the transit backbone or in a regional area, you end up with about 30 routers per region. And if you look at unique router pairs, you're going to have about 900. So what we're trying to do here is scope our problem so that we have something we can manage. A lot of people will say it doesn't make sense to do RSVP in the network because a single router can't manage 10,000 flows, and that's absolutely right. But if you segment your network hierarchically, you generally can do a lot more things like that. If you have 30 routers, you have 900 LSPs, and if you have maybe 10 LSPs per router, because maybe you have different VPNs, maybe you have classes of service, maybe you have an A to B hierarchy, you might have 10, so you go to 9,000, and in each of the regions, you might have 9,000, so there's 90,000. So a lot of folks that have systems engineering background, you can see that you probably can manage within a domain about 9,000 if you do some complex math problems I don't really understand. That means that each router at most is going to have about 9,000 LSPs going through it, but much more realistically on the order of 500 to 1,000. Okay. So what you do then in our network is you then build a mesh on the backbone such that each transit node has a full mesh of connectivity to each other transit node on the backbone. And then also in each one of the regions you build a mesh. So this gives you some really neat stuff. This gives you I guess, let me read, fine-grained control over router pair traffic flows. So one of the problems we used to run into is that when we're managing our IGP metrics, if I want to go from, this place to that place and I change something in the middle, I'm likely to affect more things than just that router pair. I'm likely to affect other things going through there as well. But with MPLS LSPs, you're actually able to take just that router pair and change it. It also gives you a constraint-based routing system. And I think someone was joking earlier that you have to have 200 engineers to traffic engineer your network. Let's make sure we understand what we're trying to do here. We're not trying to have every day a person come in and configure an LSP and tell it to go this way. You want to build this into the system so it knows how many resources it needs, and it then asks for those from the network, and it's automated. One of the tricks here, though, and hopefully something that we'll have more talks on in the future, is how do you actually build a system like that? Do you do it online or offline? And what kind of periodicity do you give to the optimization? The other thing it gives you that's real nice is really fine-grained traffic statistics. I know a lot of folks have experience with NetFlow, but one of the neat things about this is you know exactly how much traffic goes from router A to router B because you have an LSP going there, and you can actually measure that traffic. It also gives you the ability to do layer 3 hop masking, and I suppose you could say I'm an evil marketing bastard because we want to show a few hops, but that's not really the reason for it. The reason is that somebody once decided that Windows 95 only needed 32, and it causes a lot of pain for a lot of customers. And also, really, the neat thing is that MPLS provides a framework for just all kinds of nifty things. I think we need some sort of paradigm shift to make the whole internet continue to grow, and I think this is it. All right, so we're winding up here. So we started testing about 2.5 months ago. It went pretty well. We deployed code out in the network about 1.5 months ago with Cisco's and Juniper's. Production implementation was about 3 weeks ago. It's kind of a ramp-up period. Today, we have the code running on about 145 routers. We've got that WAN mesh that I was showing you on the backbone between 7 hubs. Yeah. And then there's 10 cities, so 3 more than that 7, that actually have all the routers in the hub mesh together. And then when I counted, there were 250 LSPs in production. In the New York City area, we have about 5 or 6 physical hubs or physical POPs, and about half of that is meshed together. So we're definitely in a state of transition towards this. But the busiest LSPs do about 100 megs. The one that's there is actually up at Ameritech, AADS. That's the only place where we're doing MPLS that has significant peering. One thing that I found really interesting, and it's not too terribly surprising, was that you have certain traffic flows on your cross-country backbone, say on the order of 500 to 600 megs on a circuit. That's a lot of traffic, but when you take that and you actually start deaggregating that onto particular router pairs, it goes down quite a bit. If you think about the n-squared effect of how many routers you have, it breaks down to where it's like 5, 10, 30 megs on each LSP. And we think it's pretty reasonable. This has been our goal for a long time, is at the beginning of second quarter 99 to do all of our traffic engineering and have MPLS fully deployed in our backbone, and we think we're going to hit that. All righty, so we're almost done here. Thanks to a lot of people, which will be up on our webpage later, and you can read it. Summary, it was a great opportunity. I hope that I'm presenting this more from a case study to look what we did, because this isn't what we did. This is what, this sounds really cheesy, but I mean, it's not like this is all our technology. It's Cisco engineers. It's things that, Peter, Sean, all kinds of people have really contributed to for a long time. I do think MPLS is strategic to key technologies, and I think, Peter, you need to wake up and smell that. If you have comments, you can mail it there, and we're really trying to hire a lot of people, so this is shameless, but we're having a lot of beer upstairs tonight on the 12th floor. All right, so I won't do my questions, but if you want to get everyone up here, I think we've got enough time.
Sure. Peter, do you want to come up here and We'll have both of you wrestle. No, none of that. Yeah, so first we need questions from the audience. Come on. Sure, we can get them up too. Let's see what questions we have.
This is first a question for Peter. I mean, obviously the introduction of PCS phones has degraded many of our expectations, but how did you arrive at 0.3 seconds as your target there for 2002?
Microphone technology. I went and talked to people that work with human beings and asked them how long an interruption do I need for people to realize that there is an interruption? And the human body isn't about that range. So I said, if people can't see it, I mean, the critical applications are not sending email or moving large files. The critical applications are watching TV, talking to people, where the endpoint is a human being. And if it's so fast that the human being can't notice it, it's good enough.
That doesn't seem like the target you're hitting. I mean, think about 33 frames per second in a typical movie stream, for example. If you have a jitter of up to a third of a second, that probably isn't going to look acceptable. I think you might find the same for voice over IP. So I think you might want to talk to your UI people one more time.
So what we're looking at is a 0.3 second interruption when something fails. We're expecting things to fail 2 times a year. So you may even be asleep that time, okay? If you watch the TV and it stops for 300 milliseconds, it's 11 frames that you will not see. If you watch bicycle races from France, they are having this mobile thing on a motorcycle that are looking at the bicyclists, and they're sending it up to a helicopter, and then they take it down, and then they get too shitty a signal, noise radio, they stop the signal going out. They can stop for like 5 or 6 or 10 seconds, and people still don't complain. Okay.
What about that too? I don't mean to. I'm sorry. I don't mean to like attack you or anything, but a lot of times people say, "Oh my God, it's not as good as this. It's not as good as that."
I would like to actually make a test. Okay. No, I'm not going to test on you. How many of you are willing to pay 16 times the cost of a T1 to go from 300 milliseconds to 150 milliseconds? Okay. Problem taken care of. No business.
But before I was interrupted by my sexy colleague, people often say, "Well, it's not this, it's not that," but one of the tired arguments I hear is that SONET is so great and SONET has 50 milliseconds. You should build SONET. Well, damn it, the stuff breaks, and you still have the same problems, and the routers reload, and the satellite goes away, and all that. So, the stuff we're trying to do is to get IP everywhere, to get everything that we do in communications over IP. And that doesn't mean it's going to be 33 frames per second video everywhere, because damn it, humans don't want that. They want stuff they can get convenient. They want stuff they can get cheap. Are we going to offer quality of service? Are we going to have CBR type stuff on IP? Yeah, we're trying to do that. I think we're going to pull it off. And voice over IP, it's all going to be there. But is it going to be as good as having your own optical fiber from here to there? Hell no. But y'all don't want to pay for that. So let's just get on with it.
Alan, could you talk about how you identify the backup paths and what your general philosophy is for fault tolerance with MPLS?
Could you also introduce yourself?
Steve Corbo, University of Washington.
Well, Mr. Corbato, it's been a long time. Sure. Well, okay, first of all, we don't have them today. So, and I hope I didn't mislead anyone in saying that we do have them. What we have today are the primary paths. The way that the stuff works is with constraint-based routing. And today, what we have running in the network is the ability to set bandwidth on each one of the LSPs and also set bandwidth on each one of the physical links, such that when an LSP is created, it goes from the head in throughout the network using RSVP as a setup protocol to the destination, and it creates the primary path. Now, a simple algorithm for building the backup path then is that the head end goes out and creates an LSP but keeps a record of all the routers and all of the links that it traversed on the primary path and does not traverse any of those, such that the backup path is totally autonomous with the primary path. And all of that is not really a protocol spec issue, it's an implementation issue and how you create your LSPs on the head end. One of the problems here, though, is you don't want to double allocate resources, so you have to have a way to to reserve that on the backup path, and that's where it's tricky.
Actually, I have a question. You mentioned that there are two methods to actually configuring these, either static, offline, or some type of dynamic. What are you actually doing today to configure the LSPs?
They're dynamic, so you configure it's pretty simple in both the vendors. You configure an LSP with a destination and a bandwidth, and that's pretty much all you need, and then it goes out and asks for the bandwidth from each interface with RSVP. And again, we're not talking about RSVP here for you all to use on net meeting or anything like that. It's RSVP used as a signaling protocol for the backbone MPLS. So actually what you can do is set up hierarchies such that the primary one might be an explicitly routed path along a particular manner, and then the secondary path could be just constraint-based, such that it would try to find its own way. And if that find its own way path breaks, it goes and finds its own way another way.
Okay. Thanks.
Yes, I was wondering if you had a multicast architecture in mind for your MPLS network, or if that was going to be separate from the MPLS network.
Do we have MPLS in mind? Sure.
No, you have a multicast architecture.
Do we have multicast in mind for the network? Yeah, I don't think that any of the design decisions we made with MPLS were severely impacted by a desire to do multicast. Moving packets from point A to point B, or moving packets whether you choose to replicate them somewhere along the middle. So the MPLS is an overlay forwarding system. But the thing is, one of the tricks though is it's not really a forwarding system; it's just like a vector system. So the answer is, yeah, we're going to do. We have multicast with a lot of customers today. It's not as great as Peter's stuff or Vario or a lot of other guys, but the stuff we do with MPLS wasn't really related to that.
Thanks.
How do you debug it? It probably take less time than you talked about the APS, but I don't think we have enough time. Peter asked, how do you debug it? And I said it takes less time to describe than it does to describe APS.
Okay. Any other questions? Oh, I see.
Hi, I'm Dave O'Leary, and I work for Juniper, so this is an obviously biased question, but a question for Peter. You said when you were talking about multicast that you would only deploy standards-based technology. So I'm wondering why you're using SRP in your network, or talking about using SRP.
I said standard-based technology for multicast. How I interconnect that is totally invisible to the routing protocols, because SRP from a multicast routing protocol looks like an Ethernet. Or was that a question? Somebody can give me gig Ether switches that work, I will look at it.
Okay. Thanks. Any one last call for questions? Okay, thanks. Welcome.